There, all together now. We got it. So yes, my other laptop is mad at me because I had to change my password over break, and so now it's like out of sync with respect to what it thinks my password is. So having suspected this might happen, I brought the one from home. So we're going to see how this works. But I wanted to put up our orange webpage here and point out that I've added some stuff. So the online homework system is now available. And for those of you who are familiar with it, it is exactly what you used last semester. And for those of you who aren't especially, you can get familiar with it and get 2 points extra credit in the process. I also added a little bit to it to make it describe what's happening. Okay, that's very loud. Try that again. And I made a video yesterday demonstrating how to use it. The video is about 11 minutes long. So that is the maximum time that this could possibly take you if you followed along in real time. But this is over the syllabus. It's designed to get you used to the system. So the link to it, when you log in here, go. It wants your last name as it is written in Maui. Okay, so if you have a hyphenated last name, put the hyphen in. If you have a last name that's two last names with a space, put that in. It's not case sensitive, but it is otherwise space sensitive. And if you log in and it doesn't work, please let me know, because that's what I want to fix before we start having actual activities due. Your 8-digit ID number is what is assigned to you. I would get used to entering that. So it should be on your ID card. It should be in Icon and other places as well. So you should have access to that. So once you log in, I will show you what this looks like. I have a lot of test logins. So Homework 0 is available. The rest of this page is a landing spot so you can see all of your various point totals for the semester. Also, when we do a written homework for number 4, I will return that back to you via a link inside this portal, which is why I want you to name it in a certain way so that I can generate those. So in Icon, I will have individual scores for your formative assessments and for parts of your bridge activities, but this is where you look to see like everything in one spot. So I have a separate Excel sheet that I enter the Icon grades into that I feed this into as well. The other thing about this, so I'll just click on this so you can see it if you haven't seen it. Actually, this is the one that I already did, so I don't want to do that one. I know, it'll spoil the fun. Let me open a new one. I'll be person 3 this time. Okay. So the idea of this is to be able to get data analysis practice with feedback in real time. So in future assignments, up here will be files to be downloaded, including an individual specific data set, as well as starter files in the syntax programs that I'm going to be showing you. Stata in R, but also for SAS for anyone who wants to use that. So there's no files needed here. And each of these kinds of questions, you will enter a numeric value in the box. So for instance, how many homeworks are we going to have this semester? 5. So I'm going to get it wrong on purpose. I'm going to say 8. I'm going to hit enter, and you can see what happens. The box has a red outline, meaning try again. If I hit 5, which is the right answer, and I hit enter, it turns green. So you will know that you are on the right track to doing these assignments. After you complete the numeric questions, there is a paragraph completion that forms a results section. So you will select drop-down options to complete the answers that go with the interpretation of these values. So in this case, we're talking about the syllabus. So where is my office located? North, south, east, or west are your choices. There's really only 2 viable ones. Yeah, it's technically south, but I'm in the bridge connecting the 2. So,
You're at home in your basement.
That's right. My office hours will be held.
Oh, sorry.
Yeah, from 3 to 4:30 on Wednesdays, and they will be held in my basement. So these answers are all readily available on the syllabus. If you follow along with the video, then you should get your 2 points for accuracy. One thing that the Homework 0 did not do in the past that I wanted to add this time based on feedback is to point out that these numbers up here are going to show up in your answers down here. And they will show up as zeros if you haven't entered them yet. If you get an answer wrong, so for instance, how many points total are these worth? Let's say they're worth 1,000 points.
Yay!
all of the points. So now it says 1,000 down here where it says worth a maximum of this many points. That's because it is pulling your answers, not from the answer key. But the values down here should give you context for what the box is talking about. So the last sentence says, for instance, there will be 5 formative assessments, bridge activities, or homework assignments worth a maximum of 1,000 points. So then section 2 continues and talks about software, and I will give you the answer to the very last question. This class will be super easy, a nightmare, or challenging, but in a good way. Guess what my intent is? 3, challenging, but in a good way. So you will also have a few assignments that have just standard multiple choice questions like this. So once you think you're done, there is a button to hit submit final answers. You click it. You are not done yet. Because I want to make sure that no one hits that button by mistake. So you will go down here and it will say, enter your ID to really submit, which you can choose to do, or you can hit the box that says go back and change something if you look through your answers and you're no longer happy with what you answered. And on this intermediate screen, all of the drop-down menus are gone so that you can just read through the paragraph and see if it makes sense to you. So I would like folks to give this a try. There's no late points for this assignment, but preferably by like Monday or Tuesday of next week. That way, if there's any issues with your names or your logins or anything is not quite working, I can make sure to get that ready for you before our first real homework is due, which will be towards the end of February. So I'm getting a head start on it just in case. So any questions on any of that? So homeworks 1, 2, 3, and 5 will be administered this way. Homework 4 is the one where you get to play with your own data. The other thing that I worked on is the first bridge activity, and I settled on a point structure because I had waffled on that. And I also updated the relevant slides in Lecture 0 about that. Each one of these is going to be worth 5 points. You get 3 points for doing it at all, and then you get up to 2 more based on the accuracy of your answers. Because we're going to go over the answers as a class the next day, if you turn it in late, you can't get the extra 2 points. You can only get the 3 points for doing it. So that's, but they're multiple choice questions. So Vladimir was my my tester for this yesterday or the day before. What did you think about it?
That was awesome.
Awesome.
Yeah.
That's some praise.
But with that, that's really helpful to think about how we interpret numbers.
So it's bridge 1 because I'm trying to bridge between last semester and this semester, or the last time you took intermediate or regression, wherever you took it in your discipline, and this one. So what it is 2 model outputs. One model that has only slopes from main effects of predictors, and the second model adds an interaction term. And I ask you, which of the following is true about this slope? Pick the right interpretation, or pick the right way to think about it. And so it's multiple choice. We'll go over the answers, and then hopefully you can have a sense as to what to expect on the homeworks, because they're going to be structured in a similar way, just without getting immediate feedback and discussion with the group. So I'm hopeful that this will be a new kind of activity that makes homework a little less onerous or scary to start with. That's my plan. So any questions on that? So your first one of those is due on the 3rd of February. So you've got about 10 days or so to work on that. Then we were talking about this class. That's what we were talking about. So what's this class about?
Fun.
Fun. True. Looking for something perhaps a bit more specific? What kind of fun? Generalized fun. What does the word generalized mean in this context? Not normal. Yep. So regression models are supposed to be for outcomes whose residuals, we'll review this today and in the next unit, are normally distributed. That means the outcome is supposed to be continuous and reasonably symmetric. I can't actually think of an example of a truly continuous variable in the research I've ever seen. Truly continuous with no boundaries. I can't think of anything. What we end up doing in practice is something I call continue-ish, which means it's enough, plausible enough that we can use models that pretend it's continuous. But as an extreme, a binary variable, like whether your dissertation is finished or unfinished, because those are the only two kinds. If you try to predict a slope, predicting who's likely to have a finished dissertation with some, say, personality characteristic, that slope is going to keep going and going and going and going. It doesn't understand that finished is the end line. It's going to keep going and going and going. So we need to change the model to make it understand that it has to stop between 0 and 1 to predict the probability that someone's going to finish their dissertation. Likewise, if I have a binary outcome, there is no universe in which that can have a normal residual. Can't. Not going to happen. The good news is that normal is not the only choice. In all of IntroStat, you're shown normal distributions and be like, see? See? But do you know how many other kinds there are?
Infinite.
Infinite, like many, many. So it's just a question of picking the right one. So yeah, that's what this class is about. On paper, I would say generalized models. We are also going to, let me get to the list that we ended up with. We're also going to explore, this is slide 11 where I'm starting from, multivariate models for dependent data. That's a phrase you'll hear from statisticians. What that means is when you collect multiple outcomes from a person at the same time, and you want to predict all of them at once. There has to be a way to tell the software which outcomes go with the same person, because odds are good they're going to be related to each other. So the basic assumption of independence is violated, meaning we just have to make them related somehow. So I will show you some options for doing that, and then extend that into what is known as path analysis, which is how we do multiple layers of regressions at the same time. So I have this X that predicts this W, and W predicts this Z, and this Z then predicts this Y, like those kinds of models. Yeah, they're really cool. So, and these two in particular will help you get ready to do coursework in multi-level models and structural equation models, which we'll talk about those connections a little bit today as well. So yeah, that's what this class is about. Legos, that's what this class is about, really though. So before we talk about Legos, any questions or things I should mention that I'm forgetting? Zoomers, you still with me? Okay, I'm watching the chat, by the way. Go ahead.
I just heard yes.
Yes, okay. I thought I heard something, but I didn't know where it came from. Yeah, so just for the record, for the Zoomers here, I have your screen share is what the students in the room see, and you guys are in front of my laptop with the camera. So I can talk to you and talk to you and talk to you and talk to you. It's just a fun divided attention task.
ADD.
I know. And I'm drinking water today. I'm just that excited to be here. Question? Yes. Yes, so this class is called Generalized Linear Models because we're only allowed like 22 characters or something in a name, and I couldn't like stick all the other stuff in the name. But yes, Unit 5 is going to come back to normal outcomes to start multivariate, and then we'll end with not normal outcomes in a path model. So like the whole shebang at the same time. Yep. Okay, other questions or thoughts? Can you all hear me okay? Vladimir, am I loud enough today?
That's perfect.
That's perfect. If I feel like the heater or something is really loud in here. So it's trying the best to, ooh, 16 degrees now. That's exciting. We're up there.
Yeah,
Yeah,
up by 10 from this morning.
I know. So what this class is really about though is Legos.
I had to tell my wife because she loves Legos. And
With
then she was
good
like-
reason.
And then she was like,
Well, I'm using Legos as a metaphor, but so the idea of a Lego is that there are these tiny little pieces and they come in bazillion different kinds. But the tiny little pieces can be connected to build really intricate, cool stuff. Like this is the Lego exhibit at the Mall of America that I stole this picture from. Now, why I'm talking about Legos is the same principles hold in quantitative modeling. If you understand the elemental building blocks of what goes into a statistical model, then you can rearrange it to build anything. So where this class came from and this philosophy came from is when my first job as a faculty member was in the Department of Psychology at the University of Nebraska-Lincoln. And at that time, they had no methods people. They had one person who taught all the undergraduate courses and like the first graduate course, and they needed someone to come in and teach the advanced coursework, and I got hired. And so I was like, yay, I get to teach the hard stuff, the cool stuff. And students were like, ugh. And it was a lot. It was a lot, and I didn't know how much a lot it was going to be until I was into it. And I found myself really sympathetic because it was too much new stuff at the same time. And Rebecca's like, yes, she just went through this last semester. So yes, and you're in very good company of the history of students. And what I realized is that there's this huge canyon between where like a general linear models course leaves off and where longitudinal starts, or where structural equation modeling starts, or all these advanced courses that bring like 6 new things to the table simultaneously. So students need to be able to understand what I would say traditional methods. You need to be able to understand what a t-test is, or what a chi-square test is, or what a variance is, and basic stuff like that. But increasingly in most fields, we also need to be familiar with what once were considered advanced things that really aren't anymore. Like the ceiling is so much higher as to what people are expected to know that like SEM really should be like an undergraduate course at this point, if you want to have the room to get to everywhere that you can possibly go, right? It's huge ceiling. And I feel this as someone who specializes in methods. There are certain topics that I've just had to say to myself, I'm not going to learn that. I don't have room. I can't know everything. So it's a huge ceiling. The question is, how do you connect from the more straightforward stuff to the more advanced stuff without it being overwhelming? So the solution that we were able to implement at the University of Nebraska and then subsequently at the University of Kansas is we built essentially what was the earliest version of this course. And I say we because I'm talking about my partner in crime, Jonathan Templin, another faculty member in our program, and the person who I also live with as a spouse. So we called it the bridge course. Like that's what we called it, because we were trying to bridge between the earlier coursework and the later coursework so that not everything was new at the same time. And in thinking about what would be the components that we would want to show first, we came up with this Lego-based analogy. So there are 4 Lego blocks, as we see them, that constitute most of what you would use in quantitative methods within the social sciences. The Legos that we are going to cover in this course: linear models. We started talking about that last semester, and you are going to get very good at them by the end of the semester. I can guarantee that. Next is estimation. The idea that sums of squares can only get you so far, and you'll have to understand at least conceptually how the other possible methods of finding the answers, that's what I mean by estimate, work. Link functions, which is how we tell the model to predict different kinds of outcomes that have boundaries or are only categories and not numbers. These 3 are what we're going to focus on this semester. The idea then is that once you have those under your belt, you'll be better able to pick up number 4, which I have labeled as 2 different things because it's called random effects in some contexts and it's called latent variables in other contexts, and they are indeed the same thing. So random effects are what are used in multi-level or mixed effects models for dependent data, so longitudinal data, or clustered data where you have like kids that are nested in classrooms that are nested in schools, that kind of stuff. Random effects are the same thing as latent variables, but they are talked about very differently. A latent variable is an unobserved construct that you are measuring with observed things. So if I give students a test that's measuring math ability, like I don't know what their internal ability is, I'm trying to suss that out by how they answer the questions. And which questions they get wrong tells me about maybe where their ability has stopped and where they need to continue to grow. Not just in an academic context, latent variables like sensation seeking, depression, political conservatism. Like there's latent variables everywhere that are measured by observed things. And so this Lego, these all depend on being really familiar with the first three. So the idea was to save the new stuff for separate courses, but get you ready for that to bridge the gap here with the Legos. So a little more specifically, what are we going to be hearing about then? Linear models run the world. These are the mechanism by which most research questions are going to be answered. And what do I mean by this? Well, is there an effect of a given predictor on this outcome? Is that effect the same for everybody? Or are there different kinds? Is that effect still there after we control for this other stuff that's related to it? These are the most common kinds of research questions that folks have, and linear models are designed to answer those questions. So a linear model's worldview is what I try to teach because I did not get it that way the first time. When I was an undergraduate, I learned about, for instance, analysis of variance with boxes of means, like marginal means and cell means, and I didn't understand that there was actually a model underneath those numbers. Like when you're taught a t-test, you're like, well, here's one mean and here's another, and then you do the math and but no, that's a model. So understanding how everything is a model then allows you to figure out what needs to be in your model in order to answer your questions. So I focus on it from that perspective. Last semester, we focused on one particular family of models called general linear. So there's flavors of these. It used to be that these were viewed as different things. Where the term general came from was a seminal article, I want to say 1950-ish, Jacob Cohen coined the term because he recognized how analysis of variance and regression were actually two sides of the same coin. And if you follow that line of thinking, then you can see how all of these other things that are described differently are actually connected. So if I have a model where I'm predicting a quantitative outcome, continuous-ish enough, with one numeric predictor, calling quantitative, we call that simple linear regression. Now, I don't say simple because I don't want to offend people. Like when you write papers, don't say something is easy or obvious or clearly or simple, right? Your reader is not going to like that. Two or more predictors, multiple regression. And linear gets thrown in there sometimes. It's sort of an optional word. It doesn't really mean anything. Oh, no. What if I have a categorical predictor? What I have membership in a group, like which college you're from at the university. Can that be a predictor? Sure. In that case, if I have only two groups, we would call that an independent samples t-test. If I have three groups, that's a one-way ANOVA because I only have one kind of group. If I have two kinds of groups, so maybe I'm looking at graduate students versus undergraduates across colleges, we would call that a two-way ANOVA. Can you guess what you would call three-way? Like three groups? Three-way. Four groups? Four-way. It gets really ugly real quick. You want to mix and match, have some predictors of each. Maybe they have interactions, maybe they don't. Cool. Knock yourself out. These are all one thing because they are all designed to predict the same kind of outcome. Something that is continuous, reasonably symmetric. This is all one model. So here's why. Here's our linear model. So welcome back to the world of notation. Did you miss it? It's been at least a month since you saw equations, right? I miss them. Said no one ever. So in my notation scheme, y sub I, that is my outcome for each individual. That is a variable. That is an observed variable in your data set. That is a column. Okay? Beta 0, what's that? That's an intercept. And yes, put the other word in front of it. Starts with an F.
Fixed effect?
Yep, fixed intercept. Yep, fixed effect is what these betas are more generally. They come in two flavors, intercepts and slopes. So beta 0 is a fixed intercept. It tells me when x1, x2, all the way up to xp, however many p variables you have, when these are 0, y is built just out of beta 0. Therefore, Beta 0 is my expected outcome when all these predictors are 0 when they drop out. It's like my jumping off point. The analogy I use for this is that beta 0 is the "you are here" sign of your map of your data. It tells you where you are so that you can think about where your predictor slopes move you up and down relative to that as a reference point. Beta 1 is a fixed slope. It tells you the change in y for a 1 unit change in the predictor, x1 here. In your first bridge activity, some of the distractors are going to have that wording backwards on purpose. The slope tells you the change in y for a 1 unit change in x as a predictor. In models that have more than one predictor, beta 1 tells you what we will call the unique effect, meaning what does x1 bring to the table in predicting this outcome that none of the others have. More on that in just a minute. And the reason I am putting the word fixed in front of these is because there are other kinds. Fixed means everybody gets the same. Fixed means it's a constant. That's why beta 0, beta 1, and beta 2 don't have eyes on them. They're not variables, they're constants. They are things that the model is going to figure out for you what the most likely value is given your data, spit them out in the output, and then your job is to figure out what they mean. Then, this is either known as error or residual. E for error. I like calling it residual usually, because error sounds like you did something wrong, but you didn't. Error is just, okay, so what else is responsible for someone's outcome that's not already in the story? Lots of stuff. And usually we want to know how much of the variability in y is still in this E unknown part versus what we know about. So another way of saying what the model says should happen is notation here, y hat, this little carroty thing. That means whatever the model says without the error part. So anybody who has the same value of x1, x2, all the way up through there gets the same y hat. It would be the leftover e's that distinguish them for their real values. So we're going to practice interpreting these fixed effects in the first bridge work and throughout the rest of the semester. Because the good news is that this part of the story doesn't change. I know it's going to sound crazy, but hear me out. The hard part of this class is figuring out what the hell y is, not x. Because this is just y, right? But what's coming is no. If we need to transform y in the model into something that actually is continuous, so then we're going to end up taking like the log of y and predicting that, or the logit of y, which is a new term we're going to talk about starting next week. Logits are awesome. But figuring out what version of y the predictors are operating on, that is the hard part. Everything else you learned about what an intercept does and what a slope does stays the same. All right, how are we doing so far? Okay, so no matter what kind of predictors you have, the reason that these are all flavors of the general linear model is because of what we say about E. In notation, like scary notation, you'll see it looking like this, where y, squiggle, the tilde means is distributed as, capital N, can you guess what that stands for? Or read from the slide, your pick.
I was gonna say normal distribution.
Normal, yeah. I have it unitalicized because italicized N I usually use for sample size instead. There's only so many letters, you gotta reuse them. But yeah, this says y is normal with the first spot is what the first parameter is of a normal distribution, which is the mean. Now we're saying, no, each of you gets your own mean based on the predictors. So the mean is whatever y hat works out to be from the stuff in your model that's building it. And then the variance, which is the second parameter that describes a normal distribution, is whatever the variance of the e's is that's left over. So conditional mean is what y hat is. It's the idea that it's a mean conditional on what your predictor values are. So in these models, you are told, and I told you, the textbooks will tell you, that certain things have to be plausible for this model results to be believable. The big one is that their residuals are assumed independent. Not until we get to Unit 5 in this class will we learn other choices. Up until now, we're going to work with models for independent samples. Further, everyone with the same combination of predictor values would have the same y-hat, and therefore, the model predicts equally well because there's only one residual variance. So here's a picture. I stole this picture from this place. This is the idea of normal residuals implemented in 3D space here. So one dimension here is x, like one of my predictors. The other dimension is y as my outcome. And the middle is like height. So the regression line here shows how x and y relate to each other. And so the middle, where these are here, this is what's supposed to happen. Well, it's not going to be perfect. The line's not going to fit every data point perfectly. There's going to be some wiggliness around it. So what we're saying is that the extent of the wiggliness around it is the same if you're high on x as if you're low on x. The model works equally well for everyone. More technically, that idea of constant variance, regardless of your x or your y, is homoscedasticity. I know it's terrible. Or homogeneity of variance as an assumption. You'll hear me say constant variance. Otherwise, if that is not true, like you have this kind of pattern here, I stole this picture from the link on the right. I really liked it because of their labels. On the left here, good, right? Not good. Well, not good if you're in general linear modeling land. But what if this is your data? What if this is reality? Are you gonna be like, sorry, can't do it, doesn't fit the model. Take your ball and go home? No, not on my watch. So the picture on the left here shows like evenly distributed residuals, constant variance. The picture on the right shows what happens when you predict an outcome that has a boundary at the bottom. Like if this is a count, the number of times that something happens, you have less room to be wrong as you approach the boundary than if you go the other direction. So this kind of fan shape of increasing variance as the predicted outcome increases is very, very common in count data. Turns out there's distributions that build that in as a feature, as a new expectation that's more reasonable for that kind of outcome. So we got to leave the GLM. So the normality and constant variance thing go together. The reason we assume constant variance is because the normal distribution only has one variance. That's why. So we pick a different distribution that has different ones. So how the Lego blocks fit together. In order to answer these kinds of really critical research questions using linear models on other kinds of outcomes and other kinds of sampling designs, we got to add some Legos. So my son has a bunch of Legos and he has like one of those like green squares that's like a Lego base, you know, like set your Legos on so they don't fall down. Like think of linear models as like the green base. Like you need that at a minimum. Then the question is what needs to be stacked on top of it to build the structure that you're trying to get to. So what other blocks you need depend on how your outcome is measured. That points to number 3 here, link functions, and your dimensions of sampling. If you have more than one dimension of sampling, then you need extra stuff. Now, what I mean by that, like if I have students nested in classes, some classes are different than others, some kids are different than others, 2 dimensions of sampling. That's where we need extra kinds of variance in the model to account for that. That's random effects. If I have item responses and I think they measure something that's latent, then I need to throw that in the model. But 4 is a whole separate set of classes. We're not doing 4. We're doing 1, 2, and 3. I skipped 2. 2 is estimation. Least squares is what's taught first. I don't spend a whole lot of time emphasizing. And by that, I mean the idea that the right answers in a regression model are those that minimize the e's. They make the set of e's collectively as small as possible. That's how we know what the right answers are. And the reason it's taught first is because it is what's known as a closed form expression, meaning there is a formula and that formula will always work. You can do it by hand if you had to. Not going to make you, but it is possible. That is only true for a very limited set of models in the world that you may need. So maximum likelihood is what we're using in this class. It picks up where least squares leaves off. And beyond that, Bayesian estimation, using something called Markov chain Monte Carlo, MCMC, picks up where maximum likelihood gives up. And I mean that quite deliberately. There are some models that are so complex that it can't be figured out through calculus, which is how maximum likelihood operates. So Bayesian is a different way of solving the problem and also introducing prior information about your beliefs. Now, that sounds sort of scary, but it's not. I promise. Hang on, I need to open a file. I have a little demonstration thing I wanted to do. Okay, get the file open. It's in Excel, so it can't be that scary, right? Okay. So OLS is what regression models are typically estimated using, ordinary least squares, as it's known. So the best answers, the ones that show up on your output, are those that minimize the sums of squares. How? Well, you calculate the sums of squares model and the sums of squares error and and then you end up with mean squares once you divide them by degrees of freedom, and then you have F's and all that stuff. Cool. Fine. Works great. However, maximum likelihood can do all that and more. It offers a lot more flexibility with different kinds of data. So not normal outcomes, multivariate outcomes, cluster data, incomplete data. If you have holes in your data set, you need maximum likelihood at a minimum, probably some other stuff too. It works out that figuring out the answers that make the e's the smallest is the exact same thing as maximizing what is known as a likelihood of the data, which is height. OLS calculations are computational shortcuts to a flavor of maximum likelihood called REML, or residual maximum likelihood. On your reading list is a chapter from Craig Ender's first edition of his missing data book, chapter 3. This is not the missing data class. That's a whole separate class. However, chapter 3, 4, and 5 of this book show up in every class I teach because it is the clearest explanation of how maximum likelihood works that I've ever seen in my life. This guy can write. And he uses words. Now, I'm not trying to be glib. Like a lot of stats books, it's like equation, 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 sentence, equation, 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 sentence. His is the opposite. His is like pages and pages of words, equation, picture, pages and pages of words. So I would encourage you to make the time at some point to read this because I think he makes it much more transparent. I can show you very quickly in Excel how it works though. So if you understand this, this is a tape measure. It measures height or length if you're laying down. Then you can understand maximum likelihood. So here's this thing. This is the univariate normal distribution. I stole this from Wikipedia. It has two things you have to know to describe it, a mean and a variance. So its notation is using population notation here in the Wikipedia entry. The connection to what I'm talking about is saying that y hat is the same thing as mu. Each person would have a different one potentially. And the variance of the distribution is the same thing as E variance. The y-axis of this plot is something called likelihood. You can kind of think of it like probability, but it's continuous, so that's not the right word. But it's like, how likely is this to happen? So if I'm part of this blue distribution here, and I have a 0 for my score, like that is the most likely score I can have and be part of the blue distribution. If I am part of the red distribution, 0 is still most likely. It's the tallest. But red has more variance to it. I mean, it's spread out more. So I could still have a 2 and be part of the red distribution or the blue distribution. It's just less likely. The y-axis is computed with this ugly formula. You don't need to know this. I don't know this. I don't have this memorized. I don't need to. My point in showing it to you is that it is a formula. Once you have how far off your predicted value is from the real one, that's E, and you know the E variance, then you get a number. And you have a number that says how likely your score is given the model parameters that you have. So we can check our math using software. I have a slide for this, but I wanted to do a real demonstration as well. Here's Excel. Okay. Let's say I have an outcome I'm willing to believe it's normally distributed. Cool, why not? Here's some scores. Based on math, someone has already figured out how to compute a mean and a variance. You don't have to like figure it out. There's just a ready handmade formula for it. So I can take Excel and say, figure out what the mean of these numbers is. The formula I'm using is average. Not mean, but average, of course. Likewise, I can also figure out what the variance is. That's the right answer. In maximum likelihood, the variance is going to be a little bit smaller for reasons that are not yet relevant, but point being, I know what the right answer is. So I have a column here called right height, based on the right answer. That is built from the function called normdist, normal distribution. You say, what's the number you're trying to find the height for? What's the mean? What's the standard deviation? Okay. Now these numbers are kind of little. These are likelihoods. In order to combine them, if we're willing to say that people are independent, I would multiply them. It's the same idea as in basic like probability coin tosses, right? What's the probability of getting a heads if the coin is fair? 0.5. What's the probability of getting heads twice in 2 coin flips if the coin is fair? 0.5 times 0.5. Same premise. Now what's going to happen though if I multiply these numbers together is that they're going to get really, 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 really tiny and hard to work with. So some genius figured out, hey, I can fix this. Let's just take the natural log of it. And logs mean that multiplication turns into addition. So I'm going to add up all the heights for my people in my sample here in the log scale. This is called log likelihood. The sum of those numbers is a number that describes the overall height of the data given the model parameters. It's the right answer. So this is my index to see whether or not I'm in the right place. Let's get it wrong on purpose. What if I think the mean should actually be 5.24 instead of this, and the variance should be 2? Well, under that situation, I could figure out the height of each of these things, take the log of it, add it up. Oh, this number is smaller. It's not as tall. That means it's not as good of an answer. So under the hood, what is happening is that it's like, okay, what if the mean were 5 and the variance were 10? Here's my height. Now, what if the mean were 5 and the variance were 11? Here's my height. Oh, that's taller. Okay, we're heading in the right direction. If you made it shorter instead, then you would go back the other way. Oh, well, if I went from a variance of 10 to 11 and it made it shorter, I should probably try 9 next instead of 10. So it's this iterative process that's figuring out what the optimal versions of these parameters are to make your data collectively the tallest. As you might guess, these numbers have no meaning in absolute value. Like -23 tells me absolutely nothing. It only tells me something relative to alternative versions of this. So we will use these numbers throughout the semester to judge whether we have helped our model by adding things to it. And it answers the question, did I make the data taller? If I made the data enough taller, I win. It's height. So I plotted this, the values that I've shown here. In blue is the right log height for each person, and in red is the wrong one. So you can see for certain people, it actually is taller, but it's not taller for everybody. So we're trying to be equitable and use everyone's data and try to make it as tall as possible.
That's why you have.
That's what we have. So you are going to do none of this in terms of the math, but this is how the math is working. You can take coursework in the stats department in particular if you want to know more of the nitty-gritty of how this works. It relies on calculus, because essentially what you're trying to do is get to the top of something. And if you picture like climbing the mountain at the top, my arm is flat. That means I'm at the top. So if I'm up this way, if it's a positive slope, that means I need to keep going. If it's a negative slope, I went too far and I need to go back. So Vladimir, does Jonathan talk about Newton-Raphson or any of that stuff in his classes?
Yes.
A little bit?
Yeah.
Okay. So in multidimensional latent variable measurement models, as an upper level course, you'll get into more of the nitty-gritty here, but height is the thing I want you to hang on to. The version of the model that makes the data the tallest wins. So this is what likelihood ratio tests are built on, which is how we decide which versions of the model in any kind of model. So this is one of the new things that shows up in the advanced courses that I want you to get a handle on now before you see it in those contexts as well. But here's the really, really cool part. What's so great about normal? Nothing. Who says normal has to win? Let me foreshadow. Excel has a normal distribution formula in it. It has a lot of other ones too. What's to stop us from picking a different formula for height?
Self.
Nothing. We're not tied to the normal distribution. When people say that when you have a regression model, you have to assume that your residuals are normal, it's because that is the formula being used to make height. If you pick a different formula that's tied to a different distribution, your assumptions change because then you're making a new way of defining height. That's what we're going to do. Okay, how we doing? Big picture, likelihood is height. Tallest wins. So we assume normality, independence, and constant variance because that's how we're computing height. It's that simple. So the normal distribution has only one variance in it. That's why we assume that it's constant. And if we sum the log likelihood over persons, we're assuming they're independent. But the magic of maximum likelihood is that you just pick a different formula for height, if that's what you need. Has a different probability distribution for other kinds of not normal outcomes. You can actually expect and predict differences in variance along with differences in the mean. And what if I have dependent data? Can I have that? Can I have responses from the same person that have something to do with each other? Sure, I could. That's how we do longitudinal research to measure change. You got to have some kind of baseline. You got to watch them grow. Well, in that case, the formula for height would figure out the height of each person's set of outcomes as a joint set, and then add them to another person's set of outcomes as a joint set. So it's a multidimensional height, essentially. That's coming later, not today. So we're going to pick out a new formula. That's going to solve one problem. And link functions help us make sure that we create predicted outcomes that understand what the possible range is and they stay within it. So what are the other kinds of outcomes that we can talk about? You've seen this list before. Some people talk about this as levels of measurement. This is a little bit different. This is my version of how to think about them in terms of how to predict them. So binary, zeros or ones, we can predict that. Nominal, that's unordered choices. Like, what's your favorite kind of pet? The correct answer is cat, obviously. Except that someone else is like, actually, no. So I can't rank order pets and have everyone agree on the rank order. You also see questions like this in terms of maybe most likely reaction to a situation in measuring psychological tendencies. This might be group membership, background characteristics, that kind of thing. Ordinal is a very interesting one. It's ordered categories, but often people want to treat them as numbers. They're not. They're really not. So if I have a scale ranging from 1 to 4 of strongly disagree to agree to strongly agree, you've seen these before, right? These are very common. Are these numbers? They're really not. They're labels. Because I could say 1 is strongly disagree, 20 is disagree, and I'm still right. They're still ordered. So I will show you how to predict these as labels and not numbers this semester. All of these are examples of what we can think of more generally as categorical outcomes. Synonyms for this: a discrete variable, a factor variable, a grouping variable, a qualitative variable. All of those words mean the same thing. It means these aren't numbers. Then we do have numbers, but most numbers are not really continuous. So we're going to deal with quantitative variables that have one or more natural boundaries to them, such as binomial outcomes, the number correct out of total possible. Or if you think about that and converting it to a proportion correct. What's the best you can do on a test? 100%. Woohoo! What's the worst you could do on a test? 0. Can you get 110% on a test?
Depend on the test.
Yeah, that doesn't really mean anything. Can you give 110% effort? It's a saying, right? I liken it to a Spinal Tap, turn it up to 11. That's an older reference, but they had a speaker where it stopped at 10 and they wanted it to be louder, so you should just turn it up to 11. Dude, 10 is the highest it goes. It's a whole thing. Point being, if I'm predicting proportion correct or percent correct, then my model needs to understand that the line for the regressions got to stop at these boundaries. Can't go past 0 or 1. Likewise, count data. Number of times something happened. The lowest number of times something can happen is 0. Zeros have special names. If there are no possible zeros, it's called 0 truncated. If there are more zeros than expected, it's called 0 inflated. And we will talk about these models as well. And then there's another case for censored data, meaning the ceiling happened because I ran out of money or time. Like if I'm measuring drug and alcohol recovery, and I want to know how long people are able to stay in recovery before they relapse. Well, ideally, I'd like to follow people for the rest of their lives, but my study has to have some endpoint. So hopefully, there are some people at the end of my study who have not relapsed. Does it mean they're never going to? Just means they haven't. So that's like an artificial boundary. So your model has to understand that there's a logical possibility that extends past it that you haven't measured. That's censored data. So there's a lot of instances in which numbers have boundaries, and our models need to understand that. So here's how generalized linear models work in a nutshell. Number A. Yes, I just say number A. I'm out of caffeine. It's 3 o'clock. A is link function. This is a transformation of what is to be predicted within the model. Not the data, the model. B is the same thing you already know how to do. A linear model. It's going to be called a linear predictor in your textbook, but that's what it is. So it's which predictor variables do you want to put in? Do you want to give them main effect slopes? Do you want to give them interaction terms? Do you want to give them nonlinear slopes? Like, what do you want to do? All those choices, same as before. But then how these relate to the actual data is we need to pick some other distribution, meaning some other formula for height that's not normal. Pick one that matches better. So they work for many different kinds of outcomes. Here's an example. Let's say that I have an X predictor that's quantitative, and I'm trying to predict the probability of a 1, like the probability of having a finished dissertation as opposed to unfinished. So in notation, P stands for probability. The probability that Y for any person is 1 is what we're trying to get to. Beta 0 would be a fixed intercept, describing the expected probability when X is 0, and beta 1 describes how X relates to my Y. So a regression line with a slope of, I think I put it at 1 in the other metric here, would look like this. Now, does this look cool to you or not so cool? Like at an X of 11, you have a really finished dissertation. And an X of 1, it's really unfinished. I mean, some of you are probably be like, yeah, that's me. My dissertation is really unfinished right now. I used to wait tables in college at an Italian restaurant very similar to an Olive Garden. It was called Grisanti's, and we had loaves of bread instead of sticks. And I had one family that came in every Sunday, and I waited on them. And when I left, I told them I was leaving, I wouldn't be their waitress anymore, and that I was starting graduate school. And the dad and the family said, start your thesis now. Like he was dead serious, like just start it right now. Because he was a master's student who had been in master's degrees for like 8 years or something, you know, because life, right?
Mm-hmm.
He's probably going part-time. He had a young child, another child on the way last time I checked. That kid's probably like 20 by now, I'm now thinking, but point being, start your thesis now. Ding, ding. Someone wants to start their class now. Probably someone whose internet crapped out on them and needs to log back in. Fine. No judgment here. So point being, really unfinished and really finished are not possible. So this is a little weird. So we need a line that understands the boundaries. We need a line that looks like this. Isn't it pretty? It's an S-shaped curve. A logistic curve is what it's called. Now, how did I make this? By keeping the model the same, but changing what's being predicted. This thing, the thing on the left-hand side of the equals in my model now, this is what is known as a logit. This is going to be the first thing we talk about. This is a nonlinear transformation of probability that makes it so you're predicting something that is truly continuous. But when you back translate what you predicted into the original metric of probability, it stays in the boundaries. It asymptotes at the lower and upper boundaries. Now, some genius figured out how to do this. It wasn't me. I'm just the messenger. But this is an example of how a nonlinear transformation of what Y is makes the model behave itself, so to speak. And that's what I meant about 45 minutes ago or so when I said the most difficult part of this class is figuring out what the hell Y is. Because you look at this and you're like, what? This is the log of something called the odds of the probability of a 1. That's what Y is. But you can back translate it to talk about probability. And that's what we'll do to make it understandable. So this is an example of a link function. Logits are designed for outcomes that are bounded on both sides. Another one that we will see is just a regular log, natural log, which removes the lower boundary of 0, because it's for outcomes that are unbounded in the positive direction. So problem number 1 has been solved by changing what Y is. Problem number 2 would be that a binary outcome can't ever have a normally distributed residual. Cannot happen. Good news, doesn't have to. There's a distribution for that. It's called Bernoulli. It's named after the dude who invented it. That's why it's capitalized. Like in the 1700s or something, right? This is not new. Yeah, it's a long time ago. The Bernoulli distribution gives you the probability of a 1 in binary data. That's it. So do you remember how the ugly normal distribution formula was? Let me go back several slides. This thing, this is like one of the ugliest ones there is next to beta. Hate that thing. This one, by comparison, is this. Just this little thing right here.
Mhm.
What that translates to is this function returns the probability of a 1 if that's what you got, or it returns the probability of a 0 if that's what you got. The end. And you can use the word probability because this is a discrete distribution where there's only two possibilities, not continuous where it's like infinite in between. So this distribution only has one parameter, the probability of a 1. So like for P of 0.25 here, if I know for the blue line that my probability is 0.25 of having a 1, I have to know what the probability of a 0 is. It's 0.75. And reverse for green. Cool. Now what's missing? We have a mean. What's usually next to it, like in normal land? Starts with a V.
Variance.
Variance. I don't have one of those. You know why? I don't need it. Variance is determined by the mean. The variance at any point is the mean, the probability of a 1, times the probability of a 0. The end. And so is skewness, by the way. It looks like this. If I have a variable where it's 50-50 split, that is the most variance a binary variable can have. As it approaches the boundaries, the variance shrinks accordingly. Because if everybody got a 1, there is no variance. If everybody got a 0, there is no variance. So when I predict binary outcomes, I'm not worried about variance. It's determined by the mean. I don't have to estimate it. But it's also not constant. So by switching away from a normal distribution, not only have we fixed the problem that residuals aren't normal if they're from a binary outcome, we've fixed the problem that the variance isn't constant at the same time. The right distribution will fix the problems. And there's a formula for that. So inside the same Excel sheet, I made a binary version of this. It didn't have Bernoulli as a formula, so I made one. Here's my binary outcome, where 0.6 is the probability of a 1. 6 out of 10 got a 1. Right height, that's probability of a 1 if that's what you got, times probability of a 0 if that's what you got. That little formula. Log it, sum it, here's my height with the right answer. New definition of height. One that's better suited to the data. Tallest wins under this new definition of height. That changes our assumptions. It makes sure that everything is appropriate, understanding that we have only 0s and 1s to work with. So this is what I like to think of as Mr. Potato Head. Is this still a thing? Do children still play with this?
Well, 20 years.
Maybe. Well, we were children 20 years ago, or maybe 40 years
years
ago
ago.
for some of us. How many of you have had a Mr. Potato Head in your lives? Few people? Okay, but you've seen this thing, right? The premise of Mr. Potato Head is that he just has a bunch of holes on a potato, and then you can plug in body parts and accessories however you want. And this person did it in a sensical way, but there's nothing that stops you from putting the glasses where his feet should be and so forth. So it's just like mix and match, plug things in, whatever you need. So Mr. Potato Head, if I have binary data, well, I need a logit link function, plug that in, and a Bernoulli distribution. If I have ordinal or nominal, I need a logit still, slightly different kind, but same idea, and a different distribution that means 3 categories or more instead of 2, called multinomial. Cool. What if I have proportions? Oh, that's still a logit, but since proportions are continuous between 0 and 1, that's a different distribution, some kind of binomial or beta binomial. How about counts? That's integers that stop at 0. Well, that's a log for the link to make sure it doesn't go past 0. And then these Poisson, or what's known as negative binomial, that's a distribution that allows the variance to grow with the mean. Like in the not good picture, that's what it does. Censored is something called Tobit. I know, logit, there's going to be a probit too, and a Tobit. I skipped over that one. That uses a mixture distribution of normal and Bernoulli, where Bernoulli is for whether or not it's censored, like what would have happened theoretically if you could have kept going. Skewed continuous. So things like response times, income, things that stop at 0, but they can keep going forever and ever, and they have a long tail. That would be a log to keep it bounded above 0, and then either a log normal distribution or gamma in most cases. Bimodal data, betas for that. I hate beta though, we're not doing that one. 0 inflated. That means a count or some kind of skewed distribution where you got a pile of zeros because you're talking about two different kinds of people who are part of the distribution and people who aren't. So then that would be some kind of mixture of multiple things at the same time. So this is the list. And our job is to figure out, based on what kind of outcome we have, which type of nose and feet and ears to plug in. Whichever makes the data the tallest within a family wins. All right. The good news then is that what you learned about intercepts and slopes in linear models still applies. It's just you got to change your thinking into saying this is predicting the logit, or the probit, or the tobit, or the log, instead of just y. There's a few other things that I wanted to point out that are going to change relative to what you would have seen in a standard multiple regression. So I think this is the last slide I want to do today. Let's see what's nicer. Yes, okay. Back up. So number one, in general linear models, there are specific names that differentiate predictors, like simple regression versus multiple regression and ANOVA versus regression. Those names are gone. We don't care at all what things are called based on what predictors are included. That's gone. We're directly going to predict the link transformed mean. So in logits or logs or things like that, which then we have to back translate the predictions into the original scale. So there's an extra step that happens that we have to do. And by we, I mean the software. Sums of squares are gone. Mean squares are gone. Degrees of freedom, halfway gone. But so is residual variance. E is gone. Not E the idea, but E as a representation that there is a variance and we can compute it and see how much it goes down. Like if I'm predicting a binary outcome, the variance is determined by the mean. There's not one number that I can watch shrink. So that means that R square as a measure of model effect size and prediction quality is gone. Because R square is gone, so is semi-partial R square. So we will have different ways of talking about effect size relative to what you would do in a general linear model. All parameters, so meaning things you're trying to find the values of in your model, and their standard errors are going to result from maximum likelihood, this process of figuring out which values make everything the tallest collectively. But software often does not use denominator degrees of freedom, meaning it doesn't pay attention to your sample size in trying to adjust your hypothesis tests. So that means that when we used to have a T, like we had estimate, standard error, and then T and then P, that T column is going to be labeled Z. Likewise, instead of F for multiple slopes at the same time, we will have chi-square. F times the number of slopes is chi-square. So you will see things look a little bit different, and the reference distributions are different because they're ignoring sample size. But otherwise, it's kind of the same thing. All right. No more history. Escape that for a minute. How are we doing, folks? Thumb check. Where thumbs up is excited and thumbs down is terrified. Somewhere, I'm hoping for at least level. Okay. So this is a big picture overview. We're going to fill in all the details. I just want to give you a sense as to what you're signing up for, what makes these models different from what you already know. What we have yet to talk about is how they connect to other things, but that's like 4 slides from now. We're not going to have time. So thank you for being here. Let me know if you need anything, and try homework 0 if you get a chance. Let me know if you have trouble logging in, okay? Cool. All right. Thanks, folks. Stay warm. Have good weekends.
Question. I'll let you